So we are going to start our next unit on solubility and solutions today. So our goal for the day is that we will be able to predict whether a reaction occurs between two solutions based off the solubility rules of compounds. So there are a couple of different things to unpack there. So the first thing we're going to see here is the term solution, okay? And when we have a solution, we are going to have one thing dissolved in another. That's a solid, liquid, or gas that is evenly distributed or dissolved throughout another substance. And if we think back to chapter 1, we are going to describe this as a homogeneous mixture because it is going to look the same throughout. So solutions are going to have two different parts. We're going to have a part called the solute and a part called the solvent. Okay, so the solute, this is the substance that is being dissolved. So if we are dissolving salt in water, our salt then would be our solute. Okay. Or like sugar in your coffee, your sugar would be your solute, while your solvent would be your coffee. Okay, the solvent, that is going to be our dissolving medium or the substance doing the dissolving. Okay. So in this case, our solvent, if we go back to our salt and water example, our water would be our solvent. Okay. And when our water is our solvent, we are going to have a specific name for that solution. Okay, that is going to be what we call an aqueous solution. And that's going to be a big idea in this unit because most of the solutions that we're going to be looking at are going to be aqueous. And again, that is going to be where we have water as our solvent, or where water is doing the dissolving. So for that first part of the goal is we will be able to predict if a reaction will occur between two solutions, okay? A solution, again, that's going to be any substance that is evenly distributed or dissolved throughout another. Okay, so it's going to be a homogeneous mixture. And that solution is made up of two parts, our solute and our solvent. Our solute, that's our substance being dissolved, like our salt and our solvent, that is going to be our dissolving medium or the substance doing the dissolving, such as water. Okay. So it says that we're going to base it off the solubility rules of compounds. So this introduces a new word, okay, this term solubility. Okay? So solubility is going to tell us, does something dissolve or not? So is that substance going to dissolve in that solvent? Okay? So if something is soluble, that means, yes, we are going to be able to dissolve that solute in our solvent, okay? And we can create a solution then. So soluble substance can be dissolved in our solvent, okay? So we look at aqueous solutions. If something is soluble, that means the substance can be dissolved in water. However, insoluble, that is going to be the opposite. That is going to be when our substance cannot be dissolved, and it's going to remain either a solid or a gas in that water. Okay, so like if you think about oil, okay, oil is insoluble in water because it's not going to be able to dissolve in that water. Okay, whereas something like going back to our earlier example, salt, that would be soluble in water because it can be dissolved in water. Okay? So we are going to be able to determine whether a reaction occurs or not based off of whether something is soluble or insoluble in solution. And again, we're primarily looking at aqueous solutions, so we're going to see whether a substance is soluble or insoluble in water. We'll be looking at the reaction between cobalt 2 chloride and copper 2 nitrate. Okay, so this is a double replacement reaction because we have these two compounds, and we're going to see that each of these compounds are aqueous solutions. Okay, so both of these are solids dissolved in water. Okay, so we're going to mix these two solutions together and see if a reaction occurs. Okay, so when we want to predict our products here, remember for double replacement reaction, we are going to have our two positive ions switch places so that we now have our positive copper ion bonded to that negative chlorine. Okay, copper is +2, chlorine is -1, so that forms going to be CuCl2. And then that positive cobalt, that's going to be attracted to that negative nitrate. So you end up with that copper 2 nitrate. Again, copper is +2, nitrate's -1, so you need two of those nitrates. So we're going to look to see when this reaction happens, what do we visually see? We combine a solution of cobalt 2 chloride and copper nitrate. So in that test tube right now, we have that the cobalt chloride. Okay, and when we press play, we're going to add that copper nitrate. So when we combine those two solutions, visually, we don't see a difference. Okay, so we don't have really any indication that a reaction occurred here. Okay, we don't see a change in color. We don't see the formation of a solid. We don't see any gas. We don't see any heat being produced. Okay, so looking at this reaction, when we combine the copper nitrate and our cobalt chloride, we don't see any indicators that a reaction occurred. Cobalt chloride and that copper nitrate, we didn't see any indication that a reaction occurred. So we're going to say here we had no reaction. Okay. So how come when we combined these two substances, did we not have a reaction or did we not see any of those indicators? Okay. What it do is the solubility of these products in water. Okay. So when we have this double replacement reaction, we are going to need to look at our solubility rules to see if we're actually going to have a reaction and make something new. Okay? Because in order for a reaction to occur, we must make something new. And when we're combining two solutions, our indicator that we're making something new is going to be the formation of a precipitate or the formation of a solid when we combine those two aqueous solutions. So in order to know whether or not we're going to form a solid precipitate, we're going to have to look at our solubility rules. Okay, and these rules, these are going to tell us if something is soluble in water or insoluble. And remember, if something is soluble, that means it's going to dissolve. And if something is insoluble, then it's going to form a solid, okay, or it's not going to dissolve. Okay, so we can see here that different substances are going to have different solubility rules. So if we look, our products were copper chloride and cobalt nitrate. So if we look at our nitrate rules, rule number 1 tells us all nitrate salts are soluble. So that means all nitrates are going to dissolve in water. Okay, so if they dissolve, that means that this guy is going to be an aqueous solution. Okay, we're not going to see any solid form. We're going to say dissolved in water. Okay, so we know that second product, that cobalt nitrate, that is going to be aqueous. That is going to stay dissolved in water. We're not going to form the solid. So then we need to look at our other product, that copper chloride. So if we look at rule number 3, and since that most chlorides, bromides, and iodides are soluble, except silver, lead, and mercury. Okay? So if it tells us that most chlorides are soluble, that means most compounds of chlorine in it are going to stay dissolved. Okay? Except if we have silver, lead, or mercury. So if we look at our solution here, we had copper and chlorine. That's not one of those three exceptions. So that means our copper chloride, that's going to stay dissolved in water and is going to remain an aqueous solution. Okay. So here, since we did not have any insoluble compounds or did not form any solids, that's why we're going to say here that we did not have a reaction curve. Okay. So we visually saw when we combined those two substances, that cobalt chloride and that copper nitrate, we didn't see anything change. We didn't see anything new formed. Okay. We further confirmed that by looking at the solubility rules of our products. Okay. And we saw that for copper chloride, chlorides are soluble, so that's going to remain dissolved. We're not going to form that new solid there. And same thing for nitrate. It tells us all nitrates are soluble. That means anything bonded with nitrate is going to dissolve in water. So again, we're going to remain that aqueous solution and we're not going to form a solid. So the only time we're actually going to have a reaction between in these double replacement reactions is if we form a solid or an insoluble product, because that tells us we are forming something new. We did not have a reaction occur because we did not form a solid product. Let's go ahead and look at some examples where we might have a reaction occur where when we combine our two, we produce a solid product. Okay. So for our first example, we have ammonium chloride. So that's NH4 is ammonium chloride. NH4 is +1, chlorine is -1, gives me NH4Cl. And then if we come over and look at our solubility rules to see whether NH4Cl is soluble or not, we are going to see that in our second rule, salts containing the ammonium ion are soluble. Okay, so that means anything with ammonium in it is going to dissolve, be aqueous. Okay. Something to note here is that the higher up rules supersede the later ones. So since rule number 2 says ammonium is soluble, it doesn't matter what rules 3, 4, and 5 or 6 say. Rule 2, that's our highest one up here, says ammonium is soluble, so this compound is going to dissolve. So this will be an aqueous solution. It is dissolved in water. And that's going to react with lead to nitrate. Remember that Roman numeral 2 tells us that our lead has a +2 charge. Nitrate's -1. So in order for those charges to balance, we're going to need 2 of those nitrates. And likewise, when we look at our first rule, we're going to see that anything with nitrate is soluble. So anything with nitrate is going to dissolve. Remember, soluble means it's going to dissolve in solution. So that lead to nitrate is also going to be aqueous. It doesn't matter what it says later on about lead, because rule number 1 says that nitrates are soluble, so this compound is going to be soluble. Okay, so when we're looking at these, remember, these are all going to be double replacement reactions because we have 2 compounds. Okay, so in a double replacement reaction, our 2 positively charged ions will switch. So now we'll have our +2 lead bond into our -1 chlorine. Okay, because remember, opposites attract. And our ammonium NH4 bonded to our nitrate. We need to decide which one of these products, if either, will be insoluble or will form a solid and will have a reaction occur. So we already talked about, when looking at our reactants, that anything with nitrate is soluble. Okay, so if we have that NH4NO3, that is going to be soluble or is dissolved in water, and that's going to be an aqueous solution. So now we need to look to see what will happen with our lead chloride. Will that dissolve in water or will that form a solid? So we need to come down to our rules, and we're going to see that most chlorides, so we have that chlorine, are soluble. So most dissolve. However, it says that there are exceptions containing silver, lead, and mercury. So since most dissolve, however, lead is an exception, that tells us this compound is going to be insoluble. It's not going to dissolve, and it's going to form a solid. Okay, so our product here that's a solid is going to be that lead 2 chloride. And since we formed that solid lead 2 chloride, that means yes, we do have a reaction because we formed something new here. So remember, for each of those products, we want to look at our rules, and it tells us that most chlorides are soluble or most dissolve. However, we have an exception looking at lead, so that means lead is going to be insoluble and is not going to dissolve and is going to form that solid product. And we show that by putting an S after that PbCl2. Okay. So then from here, just like any other reaction, we would need to balance it. Okay. And in order to do that, we would need 2 ammonium nitrates and then 2 ammonium chlorides. Okay. All right, so let's go ahead and look at another example so we can get some more practice. Okay, so in our first example, we have sodium hydroxide. So sodium is Na+1, hydroxide is OH -1, such as NaOH, plus silver acetate. Silver is always going to be a +1 charge, and that's found in there. It is pretty safe to assume here that both your reactants are going to be aqueous solutions because that's what we're looking at here. We're combining what happens, or we're looking at what happens when we combine these 2 solutions. Okay, but again, if we wanted to look back at our solubility rules, and we'll see that anything containing the alkali metal sodium are soluble, so it will dissolve. Okay, again, it does not matter what a later rule says because rule number 2, that higher up one, says anything with sodium will dissolve. Okay, so again, it's a double replacement reaction. So our 2 positive ions are going to switch. That means our silver with a +1 charge is going to bond to our hydroxide with a -1 charge, and our sodium with a +1 charge is going to bond to our acetate with a -1. So again, now we need to look at the solubility rules to determine which one, if either of these products, is going to be insoluble and form the solid. So we just said any compound containing sodium is going to be soluble. And that means it's going to dissolve in water and become an aqueous solution. So now we need to look at our AgOH. The first rule that kind of pops up here is going to be rule number 5. So that says most hydroxide salts are insoluble. So that means most things with the hydroxide do not dissolve. If they do not dissolve, they're insoluble. That means they're going to form a solid. Okay? When you see insoluble, think in solid. Insoluble means it's going to be in solid form. That means that AgOH, we need to show in our reaction that that AgOH is a solid by putting that little S there to show solid. Okay? So we're writing what phase these compounds are in our reaction. So again, just like in our previous example, AgOH, we formed a solid. So yes, we do have a reaction. We formed something new. Okay. And that one is already balanced, so that's always nice and easy. All right, so then let's go ahead and look at our next one. Here we have strontium hydroxide. So strontium, that's going to be Sr with a +2 charge. So we're going to need 2 of those -1 hydroxides plus cesium phosphate. So cesium's +1, phosphate is -3. We're going to have CS3PO4. Again, it's pretty safe to assume that both of these reactants will be soluble. Okay, they're both going to be aqueous solutions. But we can go ahead and check. And looking at our hydroxides, it says most hydroxides are insoluble, like what we saw with our silver hydroxide, except when we look at strontium hydroxide. So since strontium hydroxide is an exception, that means it will dissolve and it'll be an aqueous solution. Okay? And then likewise for cesium phosphate, cesium is going to be an alkali metal again, so anything with cesium is going to be soluble. Okay? So rule number 2 says anything with cesium, anything with an alkali metal is soluble, so that takes precedence over anything later. Okay, so again, this is a double replacement reaction. That means those 2 positive ions are going to flip-flop places. So that means we're going to have our positive cesium attracted and bonded to our negative hydroxide, and our +2 strontium bonded and attracted to that -3 phosphate. And because remember, opposites attract. And then still, don't forget to balance those charges. Strontium's +2, phosphate's -3. So our formula here would be SR3PO42. So to determine whether we have a reaction again, we need to look at the solubility rules. So we just said anything with that cesium is soluble. That means anything with cesium is going to dissolve and be an aqueous solution. Okay, so we're going to show that by writing the AQ. It is dissolved in water. All right. However, when it comes to phosphates, we don't have any higher up rules about strontium. So when we get to rule number 6, it tells us that most phosphate salts are insoluble. So again, if we're insoluble, that means we don't dissolve, and they're going to be in the solid state of matter. So insoluble, think in solid. So that means our strontium phosphate here, this is going to be what we call our precipitate. Remember, the solid we form, that is what we call a precipitate. So we show that the strontium phosphate is our precipitate by putting the S afterwards. So again, yes, we form something new, so we have a reaction. So whenever we're doing these, we're looking at the solubility rules to see, will this substance dissolve in water? If it is soluble, it will dissolve, then it'll just remain aqueous. Nothing's changing there. However, if it's insoluble, that means it's not going to dissolve. It should be in solid form. Okay. And then we would just need to balance this guy. 3 strontiums on either side, 2 phosphates. We need 6 of those cesium hydroxide. Okay. So then the last one we're here is with magnesium bromide. Mg has a +2 charge, Br is -1. So we'll have MgBr2. And then lithium has a +1, sulfur is -2. So I need 2 of those lithiums here. Again, we can always kind of assume that these reactants can be aqueous solutions. Okay, they're going to be dissolved in water. And again, we're going to have a double replacement reaction. So our 2 positive ions are going to flip-flop places. So now we'll have lithium bromide, each with a +1, -1 charge, and magnesium sulfide with a +2 and a -2. So we need to determine whether these salts or these compounds are soluble or not. Okay, will they dissolve in water or will they be in solid form? Okay, so LiBr, our first product, again, that's an alkali metal, and we know any compound with an alkali metal is soluble. So we know this first compound, since it has that lithium, it is soluble, which means it is going to dissolve. It's going to be an aqueous solution. Okay. So then we come over and we look at a rule for sulfides and magnesium. Okay, we don't see anything with magnesium or sulfide until we again get to this last rule that tells us most sulfides are going to be insoluble. So most compounds with sulfur are not going to dissolve and they're going to remain as a solid. Okay, so MgS, we're going to show that this is our precipitate for the solid we form by putting the S after that compound. So since that rule says most sulfides are insoluble, that means that magnesium sulfide is going to be in solid form. Okay? And since we're forming that solid, we're forming something new. Yes, we are going to have a reaction. And again, here we just need a balance by putting a 2 in front of the LIVU. All right, so there are our solubility rules, guys. We're just building off of what we looked at with double replacement reaction. Okay, so we have two compounds that are dissolved in water that are reacting with one another. And when we predict those products, we need to look at our solubility rules to determine, are we forming a solid? Are we making something new? Or are we going to still have two aqueous or two substances dissolved in water and we're not forming something new? Okay, so look at those solubility rules to see which one, if either of those products will be a solid, telling you you have a reaction. All right, please let me know if you guys have any questions. Otherwise, I hope you have a great day.